In this video, we're going to do an example of the integral test, but first I want to give an overview of the idea. And the idea is that we're trying to decide whether a given series converges or diverges. We can decide this by using the integral test. And the way this works is we have some formula for the terms of our series, a sub n. If you replace the n by x, you're going to get a continuous function. And if you integrate it, if you evaluate the improper integral from 1 to infinity, you can decide whether that integral converges or diverges. If it converges, then the series also converges, whereas if the integral diverges, then the series also diverges. However, it's important to realize that you cannot use this method on every single series. There actually are 3 conditions that tell us when we can use it. So when you write down this function f, it needs to be continuous. That means if you draw its graph, you can draw it without lifting your pencil. And in particular, that means the function doesn't have any vertical asymptotes. Also, the function needs to be positive, so it lies above the x-axis. And the function needs to be eventually decreasing. What that means is it can increase for a bit at the beginning, but after a certain value of x, it must just start decreasing forever, like this graph does. So if all 3 of these conditions are satisfied, then we can use the integral test. And the first 2 conditions, they apply to the interval of x values between 1 and infinity. So we're going to use the integral test to try and figure out whether this series converges or diverges. It's the sum from n equals 1 to infinity of e to the power negative 3n. Now, just informally, the question of whether a series converges or diverges boils down to how quickly the terms are decreasing. If the terms start decreasing quickly enough, it's going to converge. If they decrease too slowly towards 0, then it can diverge. E to the negative 3n, that's a function that's decreasing very, very quickly. It's called exponential decay. And so I expect this to converge. But we're actually going to show it converges using the integral test. So first we write down the corresponding improper integral. We just replace the n with an x. Now we integrate from 1 to infinity. The way that we evaluate an improper integral with an infinity at the top is by replacing that infinity by some letter, for example b, and then we take the limit as b goes to infinity. So we replace the improper integral with this definite integral, and then we'll evaluate a limit. Now that we just have a normal definite integral, we can evaluate it using the fundamental theorem of calculus. In this case, we end up with negative 1/3 e to the negative 3b plus 1/3 e to the negative 3. If you want to see the details on how you get from this step to that step, you should use the method of substitution where you let u equal negative 3x. We now need to evaluate the limit as b goes to infinity. The second term doesn't have a b in it. It's just a constant, so it's not going to change when I take the limit. But the first term has e to the negative 3b. And the exponential function, when you have e to the negative 3x, for example, we actually have the graph right here. If you make the x values start going towards infinity, the y values go to 0. So the limit of this first term is going to be 0. Therefore, this improper integral converges to the value 1/3 e to the negative 3. Therefore, by the integral test, since this improper integral converges, so does the infinite series that we were trying to evaluate. or trying to decide whether or not it converges. Note, this was a situation where we were allowed to use the integral test because if you look at the graph of this function, it is indeed always positive. It's also continuous. I can draw it without lifting my pencil. And it is decreasing. Those are the three conditions that allow us to use the integral test. So we have proved that this series converges. We don't actually know what value it converges to, meaning we don't know the exact value of the sum of the series. It's not this. In fact, that's the last point that I want to make. The integral test is not saying that these two quantities are equal to each other. The infinite series and the improper integral are not equal to each other. All it's saying is that if one converges, then the other converges. And also if one diverges, the other diverges. But remember, you can only use it when the three conditions are actually satisfied.